and get my screen share going. Junk on my screen. We're in March, guys. That's a good thing. All right, guys, I got 3:30. Everybody still hear me okay?
Yep.
Okay, good. Just checking there, making sure everything's good. And you see my whiteboard okay?
Yep.
All right, excellent. So yeah, let's just sort of get started here. Just thinking ahead toward lab tomorrow and what we need to do and think about. No homework due tomorrow, correct? I think that's due next Tuesday, not tomorrow, but the Tuesday after. And I did post that assignment up on D2L. We can slow down a little bit with the homeworks. I feel like I've been rushing you a little bit with them here lately. So this gives us a chance to kind of get caught up a little bit. And we may actually through today get through everything we need to for you guys to finish out that assignment, but I didn't see any point in rushing it. So next Tuesday for that. I don't think I have anything coming in notebook wise tomorrow because we're in the middle of the gravimetric analysis experiment. So we'll take that up when we get absolutely finished with it. So that's still a couple weeks out as well. And the only thing to think about is a quiz tomorrow when you come into lab. Okay, so just sort of the normal format, normal content kind of thing. All right, any questions about lab and what we're doing tomorrow? As far as stuff coming in. As far as what we're going to do tomorrow, we're going to actually collect your precipitate and we're going to isolate it and clean it and start to dry it. So that's the goal for tomorrow. All right, so let's kind of pick up with our notes again. I pretty much said everything I need to say about precipitation and gravimetric analysis. So what I want to start doing now is laying the groundwork for the next experiment that we're going to do, which is a titration experiment. So it's going to involve some acid-base chemistry, which we're going to get to, but I want to start by just talking about titrations in general. I think everybody's done a titration at some point or another. If you didn't do one in lab last semester, I'd almost bet you did one in high school. You've probably done them both places. All right, but what's the basis of a titration? Well, if we look at titration, it's an example of a volumetric analysis. So in contrast, the experiment we're doing right now is a gravimetric analysis. So you kind of know what's going on there. We're going to make a precipitate, and then ultimately we're going to isolate it and weigh it. And then from the mass of the precipitate, you're going to use some stoichiometry to get back to the amount of the analyte, which is calcium in your case, that was in your unknown. Okay, so in volumetric analysis, we're not going to weigh anything. We're going to use volume measurements to get back at the same kind of information. So remember, what we're really trying to do is determine, for example, a concentration of an analyte in a solution that I give you. Okay, so in this case with titration, we're going to make volume measurements to get at that information. Now, when we talk about a titration, the real working definition of a titration is a situation or an experiment where I've got a solution of known concentration and we're going to use that solution volumetrically to be able to get at information about an unknown. Okay, so what are we going to do? We're going to add that solution of known concentration. We're going to add it incrementally using something like a burette. to our analyte solution. Until we get a complete reaction. So in other words, just like in the case of the gravimetric analysis, we're going to have some sort of a central chemical reaction equation that we're going to be focusing on. All right. So one of those reactants is going to be a solution of known composition and concentration. And the other reactant we want to relate it to is going to be our unknown. Okay. So then we can use a stoichiometric relationship between, say, reactant and reactant to relate those two, the thing we know to the thing that we don't know. All right. And we can do this for all kinds of different reactions. So if we look at types of titrations, there's a whole bunch of different ones. One we're actually going to do is going to be an acid-base titration. You're going to do other ones as well, but we'd be focusing on an acid-base reaction here. We could also utilize a redox reaction, and some of the examples that we're going to do are going to involve redox reactions. So we're going to actually do one of those later in the semester as well as part of the lab. We could do a complexometric reaction where we form, say, a complex ion. We'll do one of those later in the semester. Good example of that, which is the one we're going to do, is going to be an EDTA titration. So you guys might remember that EDTA is a polydentate ligand from your dynamics course. And then we could also even do a precipitation reaction if we wanted to. We sort of kind of did that one in the gravimetric analysis, but we didn't do it quantitatively. All right. So we're going to focus, as I mentioned, in this case, on the acid-base reaction, because that's the one we're going to do in lab. But again, the examples we're going to do are going to be of the redox variety. And basically, you know, the procedure you use and the math you go through is the same, regardless of what type of titration we're talking about. All right, everybody good with that so far? So here's my next question. We say that when we have a solution of known concentration and we're going to add it incrementally to the analyte solution in a titration, how do we incrementally add one solution to another during the course of a titration? What tool do we use?
Burette.
We use a burette. Yeah, that's exactly right. And the nice thing about a burette is it uses a stopcock, right? So it allows us to meter the volume as it comes out and keep track of it. We also know that the burette is graduated, so it has markings on it that tell us what volume we've actually added to the solution by recording a V initial and a V final. Okay, so that's where we're going to get that volume measurement that we need. All right, so let's take a look at an example of one of these, and we'll just use the redox titration as an example. It's the one your book utilizes, so it's just kind of a good one to do. And again, everything that applies here also applies to an acid-base titration, which we'll do in lab. So here's a redox reaction. I'm not so sure this is the one the book uses or not. It may be. I can have something like oxalate ion, and we can let that react with permanganate ion, MnO4, 1 minus. Those are all in aqueous solution. And we end up getting a reaction, right? So we end up making carbon dioxide gas. We end up making some manganese ion. And we make some water. I'm going to leave the water out because we know that when we balance a redox reaction, waters come in. Well, we'll go ahead and put it in there because it is actually used as found as a product in the reaction. Now, if I asked you guys to balance this redox reaction, you guys would know how to do it, right? It's just half reaction methods. So you identify the two half reactions, you balance those individually, and then you add them back together, right? So I think there's a homework problem that I assigned you where I actually give you a redox reaction and ask you to show me how to balance it with half reaction methods, okay? Because it's just something that we need to remember how to do from last semester. But let's say we did that. So we found those stoichiometric coefficients, and here's what they turn out to be. You have a 5 in front of the oxalate, you have a 2 in front of the permanganate, 10 in front of the CO2, you get 2 manganeses, and I think you get 8 waters out of this thing. Okay, so there's a balanced redox reaction. Like I said, you guys could balance that on your own if you wanted to go back and do it. Now, let's just say, for example, that the oxalate happens to be our analyte. So we want to know how much oxalate is present in an unknown solution. So as a result, the titrant, the thing that we're adding to the analyte, has to be something of known concentration, and that has to be the only other reactant we've got, which is going to be the permanganate. So we'll label that as the titrant. Okay. Now, when we do this, what do we have to know about the titrant in order to make this happen before we ever get started? We have to know something about the titrant, right? Because ultimately we have to know something about one of those, well, let's say we have to know enough about our titrant to be able to get moles of it out. If I have moles of the permanganate, I ought to be able to get back to the moles of the oxalate using the balanced chemical reaction equation to make a mole bridge, right? So what do I need to know about the titrant in order to get back to moles of the C2O4 2-?
Concentration.
Yeah, I need to know the concentration of it. And usually we do that in terms of molarity, which is a big M. Now, what's the other piece of information that we need besides molarity to get back to moles?
Be the molar mass of it, right?
Well, be careful. If I know the molarity, I'm partway there, right? I've got the moles part, but remember what molarity is. It's moles per liter of solution, right? So to get to moles, what's the other piece of information I need?
Volume of solution.
Yeah, you need volume. So you need to know the concentration and you need to know the volume of the titrant that you're going to use, okay? Now, why do I call it the titrant? Well, because typically the thing that you know is actually what's in the burette. Doesn't have to be, but normally when we do a titration, we say that the titrant is the thing we know, and that's what we're going to put in the burette. I said, we don't have to do it that way, but that's what we'll do in this example, okay? So remember that, and I'll put the volume here in liters. Now remember in all of this that molarity times volume gives you moles. Okay, so this is how I would get to the moles of the permanganate. Now, here's the question. If I know the molarity of the titrant, and presumably we did that by either making the titrant up or we've standardized the titrant to determine in another experiment exactly what its molarity is, okay? Now, how do I get at the volume of the titrant? How would I do that in practice? I need a volume. I got a concentration and I need a volume. And ultimately, again, what I do is once I have the moles of the permanganate, I can use the mole bridge to get back to the moles of the analyte. But I need that volume. How would I experimentally get it? What's the important aspect of that volume? Remember, that's what's in the burette. How would I get that volume? How would I determine it in an experiment?
You want the difference between beginning and ending point of dispensing the titrant?
Okay, good. So I know that V dispensed is going to be my V final minus my V initial, right? Okay, so my V initial is where I started. That might be 0.000 milliliters if I'm using a micro burette, might be 0.00 or something else if I'm using a regular burette. How do I get V final? In other words, how do I know when to stop the titration? That's another way of asking the question, right?
Use an indicator.
Yeah, I need to know when the reaction is complete, because if you go back to my definition of a titration, it basically says that we're going to take something of known concentration and add it incrementally using a burette to the analyte solution until a complete reaction is achieved. Okay, so the question now becomes, well, how do I know the reaction is complete? What do I mean by that? basically we're going to treat this as a bonding level problem and say, okay, we can assume a limiting reactant here. So what does it mean? Well, it means I've added just enough permanganate to the analyte solution to react with all of the oxalate that is there. Okay, and somebody mentioned an indicator. Okay, we could use an indicator for that purpose. Okay, so we could use, to get V final, some sort of a visual indicator. So tell me about a visual indicator. What happens with that? And you guys saw one in the last experiment that we did last week, right? Methyl red was an indicator that we used, and it told us that we ended up with a quantitative pH change, right? So in this case, what is the indicator doing? I kind of already told you.
Whenever the reaction is complete, it changes color.
Yeah, that's exactly right. So when we get to a complete reaction, in other words, when I use up all the permanganate, you're going to get a color change that tells me that I've used up all the permanganate. Okay. So that's basically what I've got. In other words, when I say I use up all the permanganate, there's no more oxalate in there for it to react with. Okay. Now, the cool thing about permanganate is that it's actually a self-indicator. So it's a really easy one to explain. So let me actually tell you a little bit about that. MnO421- is in itself deep purple. It's got a very strong color associated with it. I don't know if anybody's ever seen a permanganate solution or not, but it's a very, very, very deep opaque purple. Now, the interesting thing about it is if you have a very, very dilute solution of permanganate, it actually appears pinkish. Okay. Actually, I could say pink when dilute. So the nice thing about permanganate is that it's a self-indicator. We're actually going to take advantage of the color of the permanganate to tell us when the reaction is done. Now, here's the deal. The permanganate in the burette's going to be that nice deep purple color. If I'm adding it dropwise to the analyte, which in solution is colorless, okay, what's going to happen? Well, it's going to immediately react with the analyte, and it's going to be converted to CO2, manganese, and water, all of which are colorless. Okay, so as long as the permanganate is my limiting reaction, I'm going to have a colorless solution. Okay, but what's going to happen as soon as I add 1 drop excess of permanganate and there's no more oxalate for it to react with? Well, it's going to hang around in the solution, right? There's nothing for it to react with. So what's the solution going to look like?
Will it be really pink?
Yeah, really, really pale pink. So as soon as you get a tiny, tiny excess of permanganate in there, and there's nothing else for it to react with, the solution is going to go to a really pale pink. And that tells me visually it's time to stop the titration. In other words, I've added just enough moles of permanganate to react with all the moles of the oxalate that I've got in there. Okay, so I know it's time to stop. Okay, so that's why permanganate is what we call a self-indicator. So as soon as I see that pale pink in solution, I know it's time to stop that titration. I know I'm at my, what we call endpoint. Okay, does that make sense to everybody up to this point? Now there's other ways we can do it as well, right? I mean, could also throw an electrode in there, and I could measure the potential at the electrode and look for some abrupt change in potential of an electrode. And that can also tell me where my endpoint is, or my equivalence point in this case. We're going to do that actually later on in this lab with a pH meter and a pH electrode to show that that's another way of doing it. All right. But the point is, what I'm really trying to get at here is this thing called the equivalence point in the titration. I want the equivalence point. Now, what the equivalence point represents is when the moles of titrant are stoichiometrically equal to the moles of the analyte in the solution. Another way of saying that is I've added just enough of the titrant to totally react with all of the analyte present. Okay, so now the titrant is no longer the limiting reactant. I've added just enough that the two balance out perfectly mole to mole. Okay, now, does that mean I've always got a 1-to-1 mole ratio? No. If you take a look at my balanced reaction equation up here, okay, for every 2 moles of permanganate I'm adding, how many moles of oxalate am I using up?
5.
Yeah. So it doesn't need to be a 1-to-1 molar relationship between the two. It can be anything, right? Just as long as I know what that mole to mole relationship is in the balanced reaction equation, I'm good. Okay. So that's the equivalence point. So just for grins, just to make that point, let's say that I've got 0.00136 moles of the C2O4 in my solution. Question is, how many moles of the permanganate would I have to add to fully react? Okay, so we just set up a mole bridge here, right? So we have a given. And I want to get to the moles of the permanganate I need to add, right? But I can do that because I know that mole to mole relationship through my balanced reaction equation. I know that for every 5 moles of C2O4, you guys just told me that I'm going to be utilizing 2 moles of the permanganate. Okay, so when you work this out, you see that moles of oxalate cancel with moles of oxalate, kind of a nice bonding level little problem here. And you end up with 5.44 times 10 to the minus 4th moles of MnO4, 1 minus, that you got to add. Okay. So then you could actually do a calculation. If you knew, for example, the concentration of the permanganate solution in moles per liter, you could actually back calculate a volume of that you would have to add to fully react with all of the oxalate. So that would just be a second step to this if we wanted to do that. Okay. So everybody with me more or less so far what we're doing here in a analytical titration? Any questions? All right, good enough. So let's talk a little bit about some practical considerations here. So these are things that if we're setting up the experiment, we have to think about. All right. So first one we've kind of talked a little bit about, and let's just recap it here. How do we know when the equivalence point has been reached? And we've already answered that question. First of all, we want to use an indicator. Okay. So it's something that's basically going to tell us from some sort of a visual change, like a color change, when to stop the reaction. All right, when to stop adding titrant. Now, when we use an indicator, and this is just sort of one of those things that you have to remember, what we're really measuring here is not the equivalence point, but we're actually measuring what we call the end point of the titration. And here's the interesting thing. The endpoint is nearly equivalent to the equivalence point, but they're not exactly the same thing. So we can say that they're almost equal to each other, but not quite. Anybody think of why the endpoint and the equivalence point wouldn't be exactly the same?
You have the reverse reaction.
Well, there's that. Yeah, we haven't even begun to consider equilibrium at this point. So, but we'll come to that later. Okay.
You
But again,
need-
there's some simplifying things we can say about that down the road. But just from a more practical point of view, think about like the example we just used with the permanganate being the self-indicator.
You need extra titrant to show like your phenotype of your indicator.
Yeah, that's exactly right. You've got to add a little bit extra titrant to be able to get the indicator to change color. Everybody see what I'm saying there? So in other words, when you're right at the equivalence point, is there any color change?
No.
No, because you don't have an excess of the permanganate if we're talking about the self-indicator there. There's not an excess of the permanganate in there. You have to add just a little bit more so that there's an excess of the titrant so you can actually see it, okay? But if you're really good at this, you'll find that you're talking about a difference of a half a drop or a drop or something like that, which in the grand scheme of things is not enough to worry about, okay? So the endpoint is almost the same as the equivalence point, but not quite. So in most cases, the endpoint is just a little bit beyond the equivalence point volume-wise. Okay, so we can just put that here. But for most analysis, it's good enough, okay? Now, what about like in the case of an acid-base titration where you don't have a self-indicator like permanganate, where both things that you're adding are clear and colorless? Can we still use an indicator there?
Yes, but it would have to be a different chemical.
Yeah, we sure can, but it has to be some sort of a different chemical reagent that we add separately, okay? And that's exactly what we're going to do in the case of our acid-base titration. And what ends up happening there is there's an acid-base reaction that actually happens between the titrant and the indicator that happens right around the same pH as where our equivalence point occurs. So when that happens, then we're actually going to see the color change that we want to see, but it doesn't have anything to do directly with the actual analytical reaction. It's just a secondary reaction that's going to occur that happens to give us that color change just at the right pH. Okay. So we can do this, but we have to use an external indicator in that situation. And that's what we're going to do with our acid-base titration. Okay. Does that make sense to everybody so far? Any questions? Everybody understand the difference between an endpoint and an equivalence point? All right. Other practical aspect of this that we have to think about. And that goes back to that business of needing to know the concentration of the titrant to a given precision. Now, what do you think I mean by precision here? Well, in this case, I'm talking about to a certain number of decimal places, right? To a certain number of sig figs. Let me give you an example of this. Let's say we want to do an acid-base titration. And let's say the titrant we want to use is going to be HCl. Okay. And let's say we want to make a solution that's 10th molar in HCl. Okay. You guys, matter of fact, you did that last week, didn't you, in the lab? So how would we do that? how would I make a 10th molar solution of HCl? Given that you guys did it last week, somebody remind me. What would I have to go do?
Dilute a concentrated solution or make a concentrated solution and then dilute it if you don't have one already.
Yeah, that's exactly right. We'd have to go from a stock solution, right? And then do a dilution. So it makes sense that the stock solution of HCl that we would get would be the one that we could go get out of a bottle, right? Now, stock solution of HCl happens to be concentrated HCl because that's what we get out of the bottle. Now, what is the molarity of concentrated HCl? See if you guys remember.
I think it's
12.1.
yeah, 12.1.
12.1. Yeah, 12.1 molar. Now, here's the deal. Here's how you make it. What you do is you take water and then you bubble hydrogen chloride gas into it until it's saturated, essentially. Okay. And when you do that, the concentration is around 12.1 molar. Now, here's the situation. That last decimal place, there's probably no real significance in it. So what you're probably talking about here is something that's closer to 12 molar, plus or minus a little bit. Okay. So how many sig figs do I really have here?
2.
Yeah, best case scenarios, I've probably got 2 sig figs. Okay. Now, when I'm interested in actually determining a concentration of an unknown, is 2 sig figs going to do it for me? I'm generally going to want better precision than that. Normally, I want to have 3 or 4 or maybe even 5 sig figs associated with my final concentration that I'm trying to determine. So here's the problem. I can start out with this stock solution of HCl, but I just don't know its concentration very well, right? It could be 12 molar plus or minus, 0.5 molar or something like that. That's not good enough. Okay, I just don't have enough sig figs to have the kind of precision I ultimately want in my answer. Okay, so that's a problem. Now, how do you think we might get around that? If I still want to use HCl at 10th molar concentration as my titrant, how do you think I might get around that problem? And we're actually going to do this. This is sort of a normal thing you do in a titration. And it's okay, you probably have never done this before. Well, the way we get around this problem is we do standardization of the titrant. We standardize the titrant. Okay, so what this means is that we're going to standardize it, in other words, with another reactant. In other words, we're going to do a titration on the titrant. Okay, and we're going to do it using something that reacts with the titrant that we can actually weigh out, dry, and prepare a solution of to a very precise concentration. So that thing that we use is called a primary standard. Now, a really good primary standard for doing an acid-base titration for, say, standardizing something like HCl, we're going to use something called KHP, which is called potassium hydrogen phthalate. It's a good one. But another good one that you guys might have seen before is sodium carbonate. It's called soda ash. Now, the nice thing about it is that it's a base. So that means it will react readily with an acid like HCl. The other nice thing about it is that you can buy it with a high degree of purity. Okay. It's stable to drying, so you can dry it in an oven. And the reason we might want to do that is if there's any water hanging onto it, or if it grabs any waters of hydration or anything like that, we can drive those off basically in an oven. So then what we do once we dry it is we put it in a desiccator, and that keeps the water from coming back in. Okay, so now what I've got is a very pure salt. Okay, so once I weigh out some amount of it, dry it in an oven, I usually just take way more than I think I need. I'm going to dry it in the oven, drive off any water that might be there. that I'm going to store in the desiccator. Remember, desiccator has one S and two C's. It's a funny word. Okay, and then it's ready to use. So the idea that you can dry it and it remains very pure makes it a good primary standard, which means you can get a very exact mass to lots of decimal places with it. Okay, so basically, you know, to however many decimal places your balance will go. So if we're, say, weighing out enough of it to make a primary standard solution, we could get 4, maybe even 5 sig figs out of this, which is way better than the 2 sig figs I could get out of the 12 molar HCl. Okay, so now what do? You're going to basically make an HCl solution to approximately 0.1 molar concentration. We can do that. You guys did it last time, right? So if you assume that you've got a 12.1 molar concentration, you can do a dilution calculation and then use a vol flask or something. Wouldn't even bother to use anything other than a beaker, honestly, to make up a solution that's around 0.1 molar, okay, in HCl. Doesn't need to be exact because we don't know how exact it's going to be. That's why we standardize it. Then what we're going to do is we're going to standardize it against the primary standard. Okay, so now we're going to have the HCl reacting with the primary standard, which is this. That's the Na2C2O3 or CO3, sorry. Okay, that's all aqueous. We can write this as a molecular equation here because it's easy. Just let the ions exchange partners. So you make NaCl, aqueous, and you're also going to make H2CO3, which is carbonic acid. And that, in a follow-up reaction, actually breaks down into carbon dioxide gas and water. Okay? So ultimately, it's pretty much like any other acid-base reaction you get. You add an acid to a base, and you get a salt and water. Okay? So if you balance the thing up there, you need 2 HCl's, you need 2 NaCl's. So now basically I've got a mole bridge between the two things I want. So this is my primary standard here. So I could either add a little bit of the powder, so I know exactly how much is in there, or I could make up a solution of it and take an aliquot or whatever the case may be. But now, since I know the exact amount of it I've got in there, I know the exact number of moles of it because, again, I weighed it to great precision. And then I can use my mole bridge to go back to my HCl. And if I know the volume of HCl involved in the titration, I've now got an exact molarity of the HCl. Okay, so now I can get the molarity of the HCl to 4 or maybe 5 significant figures. Now I've got a standardized titrant I can then use in another reaction. Okay, so everybody see how I did that? You use a primary standard in order to standardize or determine the exact concentration of a titrant that you otherwise wouldn't be able to do. Now, once you got that, you can use that titrant to then go off and react with another base that you want to react it with, and another titration where the base now would become the analyte. Does that make sense? Anybody ever done a standardization titration before? Was this absolutely new info for you guys?
It's new for me. I've done a normal titration on both high school and last semester, but I never standardized
the titrant. Okay. And sometimes you don't. For example, in the complexometric titration we're going to do, the EDTA, the ligand, becomes your titrant. And EDTA is very pure in its salt form. So we can actually dry some EDTA, weigh it out, and make a solution of an exactly known molarity and use it directly to titrate a metal ion with. Okay, so in that case, you don't have to standardize it. But often in an acid-base titration, yeah, you got to standardize. Okay, so this is just an example of that situation. All right, so let's take a look at an example of a standardization titration here. So this is that example I gave you guys in the handout that I sent you today. So if you have that, pull it up. Otherwise, I'll just kind of, I'll just sort of restate what I've got there. But let's read the problem first. This is titration example number 1 that I sent you. So it says a standard oxalate solution was prepared. So my standard is going to be an oxalate solution. So it's coming from sodium oxalate. That's Na2C2O4. Okay. And I'm going to use 4.1562 grams of it. And that's dried sodium oxalate. So that's stable to drying. So again, I can drive off any water that happens to be there. I can pull it out, cool it, put it in a desiccator, and then use it. Okay. So I'm going to add to that. That's going to go into 1 total liter of 1 molar sulfuric acid as my solvent. Now, why do you think I'm using sulfuric acid there instead of just water? Well, a couple of reasons. It might actually help with the dissolution of the salt. And the other reason is this is going to be a redox reaction that I'm going to utilize. Okay, so remember when you talk about redox reactions, you have to either define them as being in an acidic solution or a basic solution. So this tells me that we're defining this redox reaction in an acidic solution. So that helps us to balance it, right? So you need hydrogen ions in there. All right, so we can end up making our primary standard solution this way. So that's the first thing we do. All right, then what I'm going to do is I'm going to take 30 mils of the solution. I could do that with a pipette. That's now an aqueous acidic solution, right? And I'm going to titrate it with KMNO4. And it actually takes, to get to my endpoint, 25.22 mils of the KMNO4 solution. So that's to my endpoint. All right, so the question now is, what's the molarity of the KMNO4 solution? Okay, so presumably I want to know the molarity of the permanganate solution, because then I want to turn around and use it in another evaluation, in another titration where it becomes the titrant. So I need to know its molarity to a certain number of sig figs. Okay, so what I'm setting up here is a standardization titration. All right, so the first thing we need to do is we need to figure out what the molarity of the sodium oxalate solution is. And you got enough information to do that because we took a mass of it, right? And we know that we took it to 1 liter of total solution. So based on that information, I ought to be able to calculate a molarity for it. So let's do that. Okay, so we got 4.1562 grams of the Na2C2O4. Now, to get to a molarity, I need to convert that to what?
Moles.
Moles, very good. So I need a molar mass on that. So I could go to the periodic table and get that, right? So I know that 1 mole of Na2C2O4, or if you're in my case, you go to the internet and look it up. Turns out to be, and I did the calculation, it's about 134 grams even. Okay, so grams of sodium oxalate are gonna go away there. I've got moles now, and to get to a molarity, I need to divide my moles of it I got by my liters of it, of solution, right? So I'll put a 1 up here as a placeholder so that the liters of solution go on the bottom. Okay, so if you look at what you got there, you've got moles of the sodium oxalate per liter of solution. That's molarity, isn't it? Okay, and presumably that 1.000 liters, that number of sig figs comes from the precision of the volumetric flask that I'm using, right? So that would be a 1 liter volumetric flask. And you could actually go back in your textbook and see what the precision on a 1 liter volumetric flask is. All right, so when I do that, that turns out to be 0.03102 molar in sodium oxalate. It's also equal to the molarity of the oxalate itself, because we know ultimately when we do this, we might want to use a net ionic equation where we get rid of the spectator ions. But we can see for every dissociation of sodium oxalate, we're getting 1 oxalate ion. Okay, so I've now got my concentration of my titrant. All right, but what's my goal here? Well, I want to use this titrant now to determine the concentration of the permanganate. Okay, so now what am I going to do? I'm going to take a 30 milliliter aliquot of this stuff, and I'm going to put that, and we'll just go ahead and show this. I'm going to have a beaker or a flask down here, and that's going to have in it 30.00 milliliters of 0.03102 molar oxalate. Now, what I'm going to do is I'm going to titrate this to an endpoint using the permanganate, which is the thing I want to find out about. Okay, so this is one of those situations where the thing I know doesn't have to be in the burette. It can be down in the beaker. Okay, doesn't matter which way I go with this, just as long as I know the moles in one direction or the other. So obviously, if I have a volume and a molarity of the oxalate, I've got the moles of oxalate sitting in that beaker. Okay, so now up here in my burette, I'm going to have my KMNO4. And I also tell you in the problem that it requires 25.22 milliliters of it to get to the endpoint. So reminding ourselves what the endpoint looks like. I'll be adding the KMNO4 to the colorless C2O42- solution until I see that very pale pink develop, which tells me I have a very slight excess of the permanganate ion in there. And that's why in this situation, I'm adding the permanganate to the oxalate, because it's easier to actually see the pink develop than to see the pink go away. Okay, so always easier on our eyes to see color develop than color go away. All right, so that's why we did it this way. So now, do I have everything I need to know to get to the concentration of the permanganate? Sure I do. So in a calculation like this, we always start from what we know. Okay, so what we know is the volume and the molarity of the oxalate. So let's go ahead and write that down. I've got 30.00 milliliters of, and we'll just say C2O42- for my oxalate. So let's change it to liters here. So let's see, I got 1,000 milliliters of C2O4 per every 1 liter of it. And again, I'm keeping my identities here so I can keep track of things. So mils go away. All right, so now what do I want to do? I want to get to moles of it, right? So now I can multiply by the molarity, can't I? And I know the molarity because I made the solution up to a known concentration. So I know that for every one, we might as well keep our sig figs in here, 1.000 liters of solution. I've got what, 0.03102. Moles of C2O4. Okay, so notice what happens. Liters will cancel with liters. I'm still good to all 4 of my sig figs here. Okay, but where am I trying to go? I'm trying to get back to the moles of my permanganate. So what do I do now? I need my mole bridge back to that chemical reaction I gave you back at the top. Let's just remind ourselves. So let's see what I need. I need moles of C2O4 down here. And I want moles of MnO4 1 minus up here. What's that mole ratio look like? Oh yeah, we actually had that reaction way up here somewhere. Oh yeah. 5 moles of oxalate for 2 moles of permanganate. So I need a 5 there and a 2 there. Did I get it right, guys? I think I got it right. Okay, so look what happens. Moles of oxalate are going to cancel with moles of oxalate. I'm left with moles of permanganate. And I'm trying to get to a concentration. So I got moles in the top. So what do I need in the bottom?
Liters.
Liters. I need volume, right? So we can go ahead and do that conversion in 2 steps if we want. So it tells me up here that it takes me 25.22 mils of MnO4 to get to my endpoint, but now I want that in terms of liters. So we'll go ahead and just throw one more conversion on here. I know that for every 1,000 milliliters of it, I've got 1 liter of it. And that's MnO4, MnO4. Okay, so what happens? Mils cancel with mils. What am I left with? I'm left with moles of MnO4 2 minus per 1 liter of the permanganate solution. And that's what I want to get me back to a concentration. Okay, so when I work this out, you end up getting 0.0 to the right number of sig figs, 0.01476. So now the good thing is, this is where we'll pick up next time, is I can take that concentration of permanganate that I've just standardized, because I've just standardized it against a primary standard, and I can use it in some other analysis where permanganate is required as the titrant. So that'll be part B that we'll pick up with next time. All right, any questions about that, guys? At this point, it's just all mole-to-mole relationships, all bonding level stoichiometry here. Okay, later on, we'll talk about the implications of equilibrium, because we can't forget about that. But for now, it's really just bonding level stuff that we're talking about. Again, any questions? Everybody good? Okay, guys. That means is I'll see you in lab tomorrow. And let me go ahead and stop recording here.